Come on, what happens to a dead nuclear reactor? There are places where 1,000-ton steel beasts go to die, where men in sealed suits cut into radioactive cores with diamond-tipped saws, and where that same metal eventually ends up in surgical tables, bridges, and the cars we drive. It is the most dangerous recycling operation on the planet, and I want you to see how it works. I am taking you inside a nuclear scrapyard, where radiation-soaked steel becomes safe enough to touch. What happens to a dead reactor? Here we go. Right now, over 90 dead reactors sit awaiting dismantling across the globe. Hundreds more will join them in the coming decades. Each one holds up to 1,000 cubic meters of radioactive steel. The scrapyards that process this metal are some of the most heavily guarded places on Earth. I want you to see exactly what happens inside them. Let me give you a sense of what we are dealing with here. A single commercial nuclear reactor weighs over 2,000 tons. Inside its core, fuel rods have been cooking at over 300 degrees for decades, bombarding everything around them with neutrons. That steel does not just get dirty. It becomes radioactive at the atomic level. The official process is called decommissioning. It takes on average 15 to 30 years and costs up to $1 billion per reactor. There are 3 ways to do it. You can entomb the whole thing in concrete and wait for the radiation to decay on its own. You can mothball it for half a century and hope future technology makes it easier. Or you can go with what the industry now considers the only sensible route: prompt removal, tearing everything apart right now. Once the spent fuel is gone and the reactor is officially dead, you are left with a mountain of steel soaked in cobalt -60, nickel -63, and other isotopes. Up to 13% of the steel, roughly 1,000 cubic meters per plant, is classified as low-level radioactive waste. The rest can be decontaminated and released for recycling. But decontamination here is not a simple wash. Sections are brought into facilities like the Studsvik plant in Sweden, cut apart by remote-controlled plasma torches, then melted in induction furnaces at over 1,500 degrees. The melting itself does something remarkable. It redistributes the radionuclides, pulling most of them into the slag, leaving clean ingots that can pass clearance levels of less than 500 becquerels per kilogram. And that is where the game changes. But here's the thing nobody tells you. Some of this radioactive steel is worth more than gold. Not because of what it is, but because of what it lacks. I will show you why in just a moment. That steel is some of the purest on Earth. And the reason goes back to the 1940s. Before the first atomic bomb was tested in the New Mexico desert, the air over every blast furnace was free of man-made radioactive particles. Then we started detonating nuclear weapons, over 500 of them in the open atmosphere. Chernobyl, Fukushima, all of it released tiny isotopes that now circle the globe. Every smelt of steel produced since 1945 breathes air that contains trace cesium-137 and strontium-90. That faint radioactivity does not harm you when you walk on a bridge or drive a car, but it is a nightmare for the most sensitive instruments on Earth. A Geiger counter needs to measure 0. A medical imaging machine cannot afford false clicks. A deep space telescope hunting for dark matter must be shielded from even a few stray gamma rays. For decades, the only clean steel came from scrap merchants diving on shipwrecks sunk before 1945, pulling up armored plates from the German high seas fleet at Scapa Flow. Those wrecks were time capsules of pre-nuclear iron. But now there's another source: nuclear reactors. When the massive chunks of a pressure vessel enter a facility like Studsvik in Sweden, something extraordinary happens. They are not just washed. They are melted at 1,500 degrees Celsius in an induction furnace. At that temperature, the radionuclides behave differently from iron. Cesium, strontium, and cobalt migrate into the slag that floats to the top. The dust is captured by HEPA filters. What pours out into the ingot molds is steel with radioactive levels below 500 becquerels per kilogram. A banana has about 125. The soil in your backyard is often higher. The clean ingots are Geiger checked, scanned by gamma spectrometers, and then released under conditional clearance levels so strict that you receive more radiation from standing in the sun for an afternoon than from handling this steel for an entire year. That metal now ends up in surgical tables, in the sensor housings of autonomous vehicles, in the skeleton of particle accelerators, and in the bridges that engineers X-ray every 5 years. The irony is inescapable. The dirtiest place on Earth has become one of the only remaining sources of the cleanest steel. But here is the terrifying flip side. If a single piece of radioactive scrap misses the furnace, if a bolt with cobalt-60 ends up in a load destined for ordinary recycling, the consequences are instant and devastating. In 1983, a radioactive source from a hospital teletherapy machine was accidentally sold as scrap in Juarez, Mexico. It was melted at a foundry. The contaminated rebar was used in construction across the region and was only discovered by chance when a delivery truck took a wrong turn and passed a radiation sensor at a nuclear lab. The cleanup cost spanned years. Closer to steel mills, between 1983 and 1996, there were almost 1,900 separate discoveries of radioactivity in commercial scrap in the United States. The costs of decontamination and plant shutdowns regularly hit $23 million at mini mills, and at large integrated steel mills, the bill could exceed $100 million. A single teaspoon of cobalt-60 can shut down a billion-dollar plant for months. That is why the scrapyards handling this material are fortresses, why every incoming truck is scanned by portal monitors that would detect a single particle of radium on a wristwatch, and why the men who cut the reactors train for years to make a mistake exactly 0 times. The line between clean and catastrophe is thinner than a human hair. How they walk, it is what I want to show you next. But the scrapyard floor is not where the real danger lives. It lives in the numbers we cannot see. A single reactor vessel has been absorbing neutrons for 40, sometimes 50 years. That means the steel itself is activated. The isotopes inside are not just surface contamination you can scrub off. Cobalt-60 has a half-life of 5.27 years. After a few decades of cooling, it drops to manageable levels. Nickel-63 has a half-life of 101 years. Niobium-94 has a half-life of 20,000 years. Some of this steel will remain measurably radioactive for longer than human civilization has existed. And here is the thing that keeps regulators awake at night. Worldwide, over 90 commercial reactors have already been permanently shut down. Another 200 or more are expected to retire by 2050. That is not counting research reactors, naval propulsion reactors, and isotope production facilities. The total volume of radioactive metal that will need processing is staggering. If we simply bury it all, we fill repositories that are already politically impossible to open. If we cut it, melt it, and recycle it, we solve one problem but create another. The public hears the word radiation and their brain shuts off. The science may be airtight. The clearance levels may be stricter than almost any other industrial material. But people see a headline about radioactive steel in a hospital, and they panic. That panic has real cost. In 2009, a shipment of decommissioned steam generators from the Bruce nuclear plant in Canada was on its way to Sweden for recycling when it crossed the path of environmental groups. Protests erupted. The route was blocked. The steel was halted mid-journey and eventually had to be turned back. The generators sat in storage for years, 100 tons of perfectly reclaimable low-carbon steel, stuck because the court of public opinion ruled against physics. And that brings me to the part nobody is ready for. We need this metal now more than ever. The energy transition demands staggering amounts of steel and rare metals for wind turbines, solar farms, battery casings, and electric vehicle frames. Mining virgin ore is one of the dirtiest industries on the planet, responsible for nearly 8% of global carbon dioxide emissions. Recycled nuclear steel has a footprint that is a fraction of that. But do we trust the process? In the United States, the Nuclear Regulatory Commission's Regulatory Guide 1.86 says materials with surface contamination below certain thresholds can be released without restriction. Yet the Department of Energy itself has struggled for decades with what to do with tens of thousands of tons of scrap from its own weapons complex. The radium girls of the early 20th century taught us that companies will poison workers to save a dime. So, How do we know the same thing will not happen with radioactive scrap traders? The answer is detection. Every major recycling facility now uses portal monitors, massive gateways that scan entire truckloads of incoming metal for a single abnormal gamma spike. If a signal pings, the whole load is quarantined. Handheld detectors are deployed. The source is traced. The people who run these systems will tell you that the scariest thing they ever find is not industrial waste. It is a radium dial clock from a deceased grandmother's attic, thrown in a trash pile, triggering a lockdown that costs thousands of dollars an hour. The safety is obsessive because the price of failure is not just money. It is the invisible contamination of the entire material supply chain, a scenario that has already happened. Wait, it gets bigger. The question is not whether we melt this steel. It is where it goes afterward. And I have not yet told you about the one facility that does this differently than everyone else. A plant that operates more like a space mission than a junkyard. That is what I will walk you into next. Because when you see what happens to the slag, the dust, and the 1% that cannot be cleaned, you will understand why this is the most delicate industrial ballet ever attempted. Let me walk you through the clean room that is not clean, the facility that takes in a radioactive core shroud and pumps out certified ingot. It often starts in Sweden, at the Studsvik plant south of Stockholm, or at a similar handful of sites across Europe and North America. The pressure vessel segments arrive on flatbed trucks already surveyed by gamma cameras that map exactly which square inches are hot and which are safe. Remote-controlled plasma torches slice the steel into feedable blocks. No human hand touches the raw steel until the furnace has done its work. That work is a carefully choreographed sequence of melt, sample, pour, and certify. The induction furnace does not just heat the metal. It thoroughly mixes it. At 1500 degrees Celsius, the isotopes that activated inside the reactor vessel migrate aggressively. Cobalt and nickel concentrate into the slag, a glassy scum that floats to the surface and is skimmed off and captured as intermediate-level waste. Some isotopes also cling to the refractory lining of the furnace, which eventually becomes waste itself. The remaining liquid steel, now dramatically cleaner, is poured into ingot molds. Before it cools, a sample is drawn and sent to a shielded spectrometer that counts gamma emissions to verify the specific activity is below 500 becquerels per kilogram, often well below 100. That is the level where international regulators agree the material is safe for unrestricted release. The ingots are stamped with a unique heat number, and every single pound is traceable back to the exact reactor component it came from. Where does that steel go? Some of it ends up in radiation shielding for new medical cyclotrons, a poetic reuse where the clean steel that once protected the world from a reactor now protects a cancer patient from stray neutrons. Some is rolled into plates for the pressure vessels of next-generation small modular reactors, closing the nuclear fuel cycle physically, if not isotopically. Some becomes the structural skeleton of particle accelerators and cleanroom equipment for semiconductor fabrication, where even a handful of dust-borne radionuclides would ruin a wafer. But the truth that startles most people is that a portion enters the general scrap stream, mixed indistinguishable into rebar, bridge beams, and surgical instrument trays, not because the steel is special anymore, but because it does not need to be. It is just steel, the same alloy of iron, carbon, and trace elements that has built the world for 150 years. That is the promise the nuclear dismantlement industry has delivered. The reactors are being taken apart. The clean steel is re-entering the economy, and the 1% that cannot be cleaned, the activated slag and dust and swarf, is vitrified into glass logs and stored in concrete vaults above ground until deep geological repositories open. The volume of that ultimate waste, compared to the gigatons of mining waste that would be required to produce the same clean steel from ore, is smaller by a factor of thousands. The risk is contained, the process is documented, and the future stock of dead reactors means we are about to have a permanent supply of this material for generations. But I have not yet answered the hardest question. What happens when the person inside the suit makes a mistake? That is what I will leave you with. Here is the truth. The suits are not perfect. The plasma torches do jam. The portal monitors can, in theory, miss a stray speck smaller than a grain of sand. But that is why this industry is built on layers. The real safety is not in a single detector. It is in the fact that every melt is sampled, every ingot is traced, and every human who steps into the hot zone already knows that their worst day could be a headline that kills an entire industry. One slip, and the entire recycling chain loses public trust overnight. That pressure shapes everything. It forces these scrapyards to be cleaner than clean rooms, more accountable than banks. When that trust holds, we get something unprecedented. A world where the dead cores that once threatened cities become the steel that rebuilds them. That is the real recycling, not just of metal, but of fear into function. If you want to keep seeing how the most dangerous places on Earth operate, subscribe and turn on notifications. I walk inside them so you do not have to. I will see you inside the next vault.